my name is Paul Kiesling, and today I'll be discussing the viability and advantages of graphene production in the deep space and microgravity environment. I'm part of Wolfpack CubeSat development team, which is an aerospace team located in Palm Beach Gardens, Florida, and is composed of primarily middle and high school students. We learn about oval mechanics and participate in various aerospace projects, including building high-altitude balloons and cube satellites. In fact, in 2018, we made history as one of the first middle school teams in America to design, build, test, and launch our own CubeSat. And just last week, we launched our second CubeSat, the CapSat-1. We were able to do this through NASA's CubeSat Launch Initiative, which is an educational program created by NASA that provides students with a low-cost pathway to conduct scientific experiments in space. In addition to this, we also participate in conferences such as these and do our own research work, writing papers, so we're also able to explore our passions. And one of the things that I've been very interested in over the past couple of years is graphene, and that's what I'll be talking to you about today, and how the microgravity environment can enhance graphene production. So obviously we've made significant progress in space exploration over the past century, from sending the first humans to the moon to building and launching telescopes that can see back to the beginnings of the universe. And as private companies and space agencies continue making plans to send humans back to the moon and onwards towards Mars, creating a long-term interplanetary settlement proves to be one of the most challenging technical enterprises in human history. And when thinking about how we're going to create these interplanetary settlements, one of the main focuses needs to be on sustainable development, and specifically the creation of sustainable space missions. In order to create sustainable space missions, one of the necessities is putting more research into materials science to see what materials can help aid our exploration of space. And these materials must also be extremely lightweight and resilient in order to survive in the harsh conditions of space that combine extreme temperatures, ionizing radiation, and micrometeorites. One such material is graphene, which is commonly known as the wonder material due to all of its various applications and many things, including ultrafiltration of water and energy production and storage, as I'll talk about later in my presentation. Graphene was originally discovered in 2004 and is a 2D allotrope of carbon, which means that it's all the same atoms as carbon, just rearranged in a different way. And graphene, even though graphene was discovered in 2004, it's still not widely implemented commercially due to the various production challenges associated with graphene. However, a lot of these challenges in large part root from the microgravity environment, root from gravitational forces, such as convection, which means that graphene is unique not only because of its broad applications, but also because there's a possibility that it can be more effectively produced in the microgravity environment, meaning that it could be much easier for it to be used in various applications within space exploration, as it can be produced on orbit in space. So graphene's popularity grew exponentially after it was responsible for the 2010 Nobel Prize in Physics. This great feat all began when a group of scientists believed that they could study carbon nanotubes in an unfolded configuration, and they originally planned to polish down a graphite block to 10 layers thick. One of the ways that they found that they were able to do this when they were in their lab was by using a piece of Scotch tape and adhering it to the graphite block, and then they realized that they could progressively amass thinner flakes of graphite. Once they dissolved the tape, they're ultimately able to isolate graphene. So the main reason why graphene hasn't been commercially implemented, as I mentioned earlier, is due to all of the production challenges. Typically, the majority of production methods only produce a very small amount of graphene, and the ones that are easily scalable generally produce lower quality graphene, which can limit some of its qualities, such as conductivity and other things, making it harder to use in applications and decreasing some of its benefits. But despite the production challenge, so in order to understand how we can start implementing graphene on Earth and in space, we must not only understand the implications of various production methods, but also see how the microgravity environment can help to enhance some of these production methods, and how we can use the phenomenon in microgravity to help graphene production. There are many common production methods here on Earth, and I will focus on three in my presentation today: mechanical exfoliation, liquid phase exfoliation, and chemical vapor deposition. Mechanical exfoliation is also known as the Scotch tape method and was the method that was first used in 2004 to isolate graphene. The mechanical exfoliation method primarily focuses on isolating monolayer, bilayer, and few layer thick graphene flakes. So the way that this method works is a crystal graphite is peeled apart many times with tape until there are flakes of graphene left adhered to the tape. This adhesive tape is then pressed against the substrate and peeled away, which produces small quantities of very high quality graphene. However, the small quantity of graphene produced renders it unsuitable for commercial applications. Secondly, as an alternative to mechanical exfoliation and to produce larger quantities of graphene, the liquid phase exfoliation method was developed in 2008 and has been extensively researched ever since. In this method, graphite flakes are immersed into solvent and subject to ultrasound to shake the graphite apart into graphene flakes. And a portion of the graphite sample is also exfoliated into graphene flakes that are suspended in the solvent. The majority of there's some graphene flakes in the solvent, but the majority of it remains in the form of graphite, which is then removed using centrifugation. So even though this method is highly scalable, the main problem is that the graphene produced is of lower quality, which makes it harder to use in various applications and limits the benefits of this material. Finally, chemical vapor deposition, or CVD, is not only used for graphene production, but also to produce various polymers. So CVD is used to create long sheets of graphene, which makes it much more suitable for applications and for industrial applications. In this method, it starts with tanks containing an initiator material and one or more monomers, which will form the building blocks for the polymer coating. And then these coatings are then vaporized and then introduced into a vacuum chamber, which contains the material to be coated. And then this ultimately creates graphene. And the initiator helps to just speed up the process by which the monomers link up and change to form the polymer. The main problem with this is also the low quality of graphene produced, as I mentioned before. Despite the production challenges on Earth, an emerging interest is how graphene can be produced in the microgravity environment. The microgravity environment alters many observable phenomena within the material and within the physical and life scientists, and therefore an emerging interest with the material science is how the microgravity environment can impact the formation of various materials. Specifically, one of the main problems with forming materials on Earth is convection. Essentially, convection is the process by which liquids in an experiment are able to form based off of the forces of gravity, with more dense materials sinking to the bottom and displacing the less dense liquids and materials on top, which generally creates a less pure and worse performing materials. However, in microgravity, there's much less forces acting on the liquids in the experiment and the materials, which generally leads to the creation of more pure and better performing materials. So now I'll discuss the different production methods for graphene that can be enhanced for the microgravity environment. And so if these methods can be proved to effectively create graphene in the microgravity environment, then it will open up a venue for not only producing graphene in microgravity, but also utilizing it in various space applications to help propel space exploration. So the first method that can be adapted for the microgravity environment is the arc and liquid method. So the primary advantage of the arc and liquid method is that it is simple and space and cost efficient, which also obviously makes it great for space exploration, where there's not that much space to put large labs and facilities that are generally needed to produce graphene. Theoretically, all that is necessary for this method is a DC power supply, a graphite electrode, and a container of liquid nitrogen. And most importantly, this method can be easily scaled to produce high yields of nanomaterials. This method specifically targets the production of graphene, but can also produce other related nanomaterials, including graphene. So as I mentioned, this method requires minimal materials in order to produce graphene. It starts with carbon electrodes. The anode and the cathode are first submerged into a liquid solvent, and then the arc is catalyzed by contact with these carbon electrodes. The temperature in this area of the arc is then set much higher than other parts of the arc, which creates plasma and a significant thermal gradient across this area. This plasma then causes the evaporation of the anode, which generates carbon vapor that is quenched by the thermal gradient, thus producing carbon nanotubes and other related nanomaterials. The primary part of this process that is affected by gravity is creating a stable thermal temperature distribution across the water in the arc. Due to convection, it is much harder to create this. It's much harder to create this thermal gradient and to keep it stable, which generally leads to the creation of less pure carbon nanomaterials in graphene. However, in microgravity, where there is not as much forces acting on the water, it's much easier to create a stable thermal gradient, which then leads to better quality production of graphene. Recently a NASA study tried to quantify how much the microgravity environment to quantify how much convection impacted the formation of carbon nanomaterials in this in the arc and liquid method, and see how microgravity could help that. In order to do this, they created a simplified arc and liquid apparatus, and then used the drop chamber to simulate the microgravity environment. This presents a series of challenges in and of itself, just because since the drop chamber, there's obviously only a limited amount of time that the experiment can be conducted, so they're only able to collect 2 to 3 seconds of data, meaning that the experiment's not as thorough as it could have been. However, it was still found that the microgravity environment can positively impact the formation of carbon nanotubes in the microgravity environment. Furthermore, so a way that this experiment can be expanded upon in the future in order to gain more results is by conducting it on the International Space Station, or constantly through small satellites such as CubeSats. One of the ways this would provide more data, which could help advance our understanding of how nanomaterials can be and graphene can be produced in the space environment, and then also applied. Another production method is graphene aerogel. Similar to graphene, aerogel is another unique material that many scientists are researching. Aerogel is essentially created when the liquid component of gel is removed and replaced with gases, which creates an ultra lightweight material that's very low density. In fact, it is widely considered one of the lightest materials known to man, as it can even sit on the petals of a flower without deforming them. Graphene aerogel is just a combination of aerogel and graphene. Essentially, it has the electrical conductivity of graphene, just in the extremely lightweight form of aerogel. There are 2 primary steps in creating graphene aerogel. The first is to create the graphene hydrogel. In order to produce the graphene hydrogel, graphene oxide flakes are placed in aqueous solution, and once the graphene oxide dispersion is created, it can be placed into a furnace and heated, which creates the hydrogel. And then to create the aerogel, the liquid component of the hydrogel is removed, leaving just air in the structure. The primary part of this process that is affected by gravity is the creation of the graphene oxide dispersion, because due to gravity, it pulls the graphene oxide flakes and water down, which creates an anisotropic or unevenly distributed graphene hydrogel, and then ultimately an unevenly distributed graphene aerogel. However, in microgravity, where there's not as much forces acting on this dispersion, it creates a more uniform macrostructure in the hydrogel, leading to a more pure and better performing graphene aerogel. So ultimately, since graphene can be more effectively produced in the microgravity environment, a logical next step would be to use graphene in various space applications. Specifically in this presentation, I'll focus on 2 of them, in energy production and storage through graphene-based supercapacitors and solar cells. First, when thinking about capacitors, there are 2 primary systems that are used for capacitive energy storage. First is electrical double-layer capacitors, EDLCs, and secondly, it's pseudocapacitors. EDLCs have a good life cycle. However, they have a relatively low specific capacitance, whereas pseudocapacitors have a high specific capacitance but poor stability and slow charge discharge rates. Graphene could primarily be utilized in EDLCs. However, there's an emerging class of capacitors called hybrid supercapacitors, which aim to utilize both of these capacitors to maximize their benefits and limit their disadvantages. And graphene can be a very attractive electrode for this due to its electrical conductivity. Recently, prototypes of capacitors made here on Earth with graphene have shown that graphene-based supercapacitors can significantly enhance energy storage relative to regular supercapacitors. So if graphene is proved to it can be more effectively produced in space, then graphene-based supercapacitors can be another means of energy storage in space. Another one of the revolutionary applications of graphene could be its use within photovoltaic cells. Recently, a team of engineers from MIT found a way to make graphene-based photovoltaic cells that collect 100 times more power per weight unit than regular photovoltaic cells. There are numerous applications for graphene within photovoltaic cells. First, graphene can be used as a conductive electrode. Graphene is widely considered to be a great replacement electrode for indium tin oxide, which is what's currently used for most solar panels. And the really unique thing about graphene relating to photovoltaics is that they can be used to create ultra lightweight and also transparent and flexible solar cells, which could be very great for space applications, as since they're so lightweight, flexible, and transparent, it can make it much easier for astronauts to handle. Secondly, graphene can be used as an electron transport layer for photovoltaic cells, which would take advantage of graphene's high electron mobility. So ultimately, as I mentioned before, graphene photovoltaic cells could be specifically unique for space applications, since they're very lightweight and flexible, meaning that astronauts can handle them easier. So using graphene, if graphene can be produced on orbit and then ultimately utilized in space panels, this would accomplish two primary purposes. First, it would provide proof of concept that graphene-based solar cells, that graphene electrodes can be used as a replacement for indium tin oxide electrodes, which would open up a venue for further research and production on Earth. And secondly, it would prove that graphene-based solar cells and solar cells in general can be produced on orbit, which would provide astronauts with another means of making energy in space for future space missions. So ultimately, the start of the space era was ignited by the creation of rockets and various materials, and further success within space endeavors heavily relies upon the creation of new materials that have outstanding properties that can survive in the harsh conditions of space. So as we keep looking to send humans back to the moon and onwards towards Mars, and ultimately create interplanetary settlements, acceleration with the materials sciences will also have to accelerate its innovation. Thank you.